Now that we're done with defining what our project is about, let's go over some project goals in the second part of this video. Early on, it was important to us to choose a design that was realistic to make within the semester, achievable with on-campus resources, and unique in its application. After considering various options, we decided to make an egg cutter. It was not only the most feasible, but also offered room for improvement over some of the existing signs that we found online. Originally, our goal was to create an egg cutter that could make uniform cuts anywhere on the egg, not just the top. Additionally, we aimed to design a cutter that could achieve a clean cut in one motion, eliminating the need for the twist-off step. We also wanted to reduce the pressure points by adding a smaller, more numerous teeth for a smoother, more consistent cut. Finally, we also wanted to make our original designs out of metal, as we thought that would be a better material than many of the other things that we saw. Material selection was really important at this stage of the process. It would decide what we were using to make the actual project. It would decide how we designed it, and it would decide where we printed it. Since an egg cutter doesn't require extreme strength, we had more flexibility in our materials. However, the frame still needed to be really light and sturdy, while the blades needed to be able to cut without breaking. Our initial designs used metal, specifically stainless steel and aluminum, because of their strength and their water resistance. Unfortunately, we encountered some pretty big setbacks, though. On campus, there are only a few ways to make something out of metal, especially something as precise and small as what we're making. We have a laser cutter, a milling machine, and a 3D printer lab. To start, laser cutters are high-powered lasers capable of burning through steel with really high precision. This option was our first choice by far. We wanted to use this so bad, as it would allow us to work with really high-quality steel, and it would make our project extremely durable and smooth and just generally really usable. Using a stainless steel composite would be best, as it's very water resistant, perfect for the kitchen, and its heat resistance is also really high, so you'd be able to hold it while still not feeling the heat from a boiling egg that just got out of the water. Unfortunately, the only laser cutter on campus broke down earlier this year and won't be getting replaced until November or December, according to staff at the cutter lab. The work order hasn't even gone through, as to our knowledge, but we hope that maybe we can at least get one prototype if we're lucky. At this point, though, we've kind of abandoned all hope for that and are just focusing on getting the current design finished and out of the way. Our next idea was the school's water cutter. So a water cutter is a high-pressure water jet system capable of producing enough force to a surface that it cleanly cuts through it. We wanted to use this as it would have allowed us to keep using most metal materials, and we're, again, very set on using metal materials initially. Unfortunately, the lab technician told us that many of the parts that we had modeled were just too small, and many parts would have to be redesigned, otherwise they'd be destroyed or broken in construction. And then, just to top it all off, the water jet in our lab has been malfunctioning, and now the nozzle needs to get replaced. So, in the end, we kind of just realized that any usage of metal in our project would have to be pre-made or store-bought, which was a little frustrating, but we got over it pretty fast. Because it doesn't seem that the school wants us to use metals in our project, we have to resort to using the 3D printer lab. There are a few different types of printers there. There are resin printers, high carbon plastic printers, and PLA or polylactic acid printers. Due to the size and moving complexity of our project, our peers over at the 3D printer lab recommended that we use either the resin printer or the PLA 3D printer, which is pretty standard 3D printer. Resin printers use ultraviolet light to quickly harden filament in a basin full of material. The resulting 3D print should, in theory, need less scaffolding, which comes with the trade-off of needing more time for the object to cure. Resin is generally stronger than PLA by a pretty significant margin, so we thought that it would probably be best for us. So going a little bit more in depth into the stress strain curve for these resin materials, for AMD3, which is a common one, we can see that the material has a very high tensile strength. It means that it's a stronger material capable of withstanding greater forces without breaking. It's very good for high load applications, but it comes with the drawback that it's pretty brittle. If you drop it, it might have a chance at cracking or even snapping. Resin is best used in structural components and just anything that doesn't really move. It's not made for mechanical purposes. It's not the best for that. And we'll get to see that later. We ended up using this product for our second prototype, which we'll discuss in a couple minutes. Ultimately, we decided on using the standard MakerBot 3D printers using PLA or polylactic acid, which we actually used to make our very first prototype. Now, PLA is kind of flimsy. We'll talk about it a bit more in depth soon, but generally it's considered to be pretty flimsy, pretty standard plastic material used in almost every 3D printer. But it being a plastic means that it comes with its own array of benefits. So it's very cost effective, it's super cheap, it's light, it's flexible, it's durable, and it's resistant to corrosion. It's just a good material. Though it can be a pollutant, there's a reason why we use plastic basically in everything. Going a little more in depth on PLA. PLA is actually biodegradable too, which is derived from totally renewable sources such as sugar beets and corn. It decomposes in water, carbon dioxide, and humus, the black material in soil. So it's actually not a pollutant. It's used in a lot of 3D printers because it's not as toxic as a lot of other plastics. And on top of that, it can be manufactured easily using existing plastic infrastructure. Looking at the stress strain curve pictured, it is a lot weaker than a lot of the other materials that we've talked about, but it still gets the job done. At the end of the day, we're just making an egg cutter. An egg cutter doesn't need to have 100 megapascals of resistance. It's just not necessary for what we're looking for. We still can easily cut an egg using the material provided and without damaging the blade even remotely. It's just not an issue. The other materials depicted in this graph are higher carbon versions of PLA, or composites of PLA, I should say, and are generally available to us. However, due to what we are making and kind of the size and difficulty of the print, it wasn't recommended to us by the lab to use higher carbon materials as they have trouble getting off of the actual printing machine. Ultimately, at the end of the day, we're making a stress cutter, specifically an egg cutter. So it doesn't need to be the most structurally stable. It doesn't need to have the strongest materials. It just needs to get the job done, which is job being to cut the top off of an egg and to make a single or, I guess, multiple dishes. Using metal or using these super advanced methods of manufacturing are just not as necessary for what we're doing. We overthought what materials we needed. We dreamt a little too big, and even if, we still want to use steel, we still want to use aluminum, we still want to use resin, these materials at the end of the day are overkill, and PLA is really the baseline of what we need.